Hello, can you hear me? Do say hello if you can hear me in the room. We should be ready to go any minute. If you're joining us from the live through YouTube, do check out the questions. The information below the YouTube screen, and come along and check out the quick questions chat. You'll find all sorts of resources. We're now here at Doc Clay's chemistry pages. You'll come through to the home page. If you're on the home page, just click on the quick questions link at the top there. It will take you through to Doc Clay's quick questions. If you want to join the website, you'll find revision webinars on Monday and Thursday evenings. And there's also a list of the past webinars there. There's all the resources for today's videos, and also if you're a member and want to get hold of any of the question sheets that we got for today's session, you'll find those in the past webinars section. They're in quick practical questions for the 26th of April 2017, and you can find them here. There's a OneNote pages, but here's also the questions on titrations and enthalpy questions. These are designed to be short webinars. They're only going to be about 15-20 minutes long at most, so I'm not going to keep you very long, and we're just going to go through in these sessions some of the practicals that you need to know for the AQA A-level chemistry exam that you've got coming up. So just to point out where that information is on our site, if you're in the A-level course, to note there are 12 of them in total for the A-level that you'll be sitting. Do check them out. Videos have been made on all 12. We're just going to be going and having a quick look at some of the first two today. So let's go and start having a look. So here we are. If you log in, you should be able to get these questions, and also even if you haven't, you'll be able to get access to the OneNote page here, where we've got lots of information. Practical questions on titrations and enthalpies. These are the first two practicals that we need to know about for the required practicals. Here is a list of all 12. So the first 6 are shown here. You'll find those are from your AS course. So we got here, these are all from AS year 1. So you've got to be able to recall those first 6. Acid-base titrations and enthalpy changes are the ones we're going to look at today. How the rate of reaction changes with temperature, we'll look at those next week most likely, and we'll also look at the A-level initial rates and monitoring method. You've got to know the test tube reactions, and then we've got 2 organic reactions at the bottom here, distillation of products from a reaction and test for alcohols. They're from the AS. Then at the bottom here, we got the final 6. These are all year 2 practicals. And these are looking at measuring rates of reaction, measuring the EMF of an electrochemical cell, investigating how pH changes with a weak acid, preparation of organic solids, and carrying out simple test tube reactions, and finally separation of species by thin layer chromatography. These practicals could come up in the paper 1 or the paper 2 in any format, and certainly look like they're going to be prevalent in the paper 3, with a large number of marks coming in the paper 3 on your practical chemistry. Let's have a look then at, we're at 4:15 now. I think we'll run and we'll have a quick look and see what we have got going on in terms of the experimental details. Like I say, we've got 2 practicals we're going to look at this afternoon. We've got the first one, experimental details, and these are what we've got to be able to recall. They could ask us about those, is how to make a standard solution. So this is all part of the first practical that you need to be able to do. And we've got our details here of how we do that. So you need to make up a standard solution with a known amount of moles and add water up to a known volume, essentially. We do things like rinsing as we go through to ensure that we keep clean, and also to ensure all substances get washed. Sorry, my screen's causing a bit of substances wash through. So in other words, so we don't leave any behind. And then we add here drop-wise to the top of a meniscus, just to take care so we don't overshoot when we're making a standard solution. If it's been a while since you made a standard solution, remember a volumetric flask looks a bit like this. You've got a line about there, and then you're filling up to the meniscus up to that point. Remember as well, the meniscus is sort of the little drop of the water, and it's when you've got just the bottom of the meniscus is when you're touching the line. So there we go. That's how we make a standard solution. I'm not going to read through those in too much detail. Then if we want to do a titration, we have to use certain bits of kit. We need to use pipettes to measure out exact volumes of solution and transfer them into conical flasks. You're always going to use an indicator. These are an acid-base titration here. You, of course, saw redox titrations last year. You're going to add the volumetric solution to the burette using a funnel. That's going to avoid spillages here. Record the start volume to 2 dp. So when you're doing any of your measurements with your titrations, you're going to measure them to plus or minus 0.05 centimeters cubed. You're going to titrate the solution from the burette, and we use a burette here because we can get variable solutions or variable volumes, whereas a pipette only gives us one volume at a time. So we can't use a pipette for a titration. And then we wait for a change in indicator, record the final reading to 2 dp, and we repeat until we have concordant results. So they're the important key details, again, that we'd need to be able to recall for doing a practical. And then the second practical we're going to look at here is how we actually go about doing an enthalpy change reaction. So here we're doing an enthalpy change where we're measuring the change in energy somehow. Q equals mc delta T, where we got the mass of the water. This is always the mass of the water. We've got the heat capacity of the substance that we're heating, and we've got a change in temperature. Again, sorry, my screen, that here should be delta T at the end. We've got two ways of doing this. We can do an enthalpy of neutralization, where you've probably done this with sort of a polystyrene cup, or we can do bomb calorimetry. Now, bomb calorimetry you may well have done with sort of a tin can with some water in, and you may have had sort of a fuel burner that you had on underneath, and you lit the fuel, and then you heated the water in the tin can to a certain temperature. Both of these are ways of measuring the enthalpy change. We always have to be aware that we'll lose heat, or there's heat loss to the surroundings in both of these experiments is an issue. And also when we're mixing solutions, we don't want to spill anything. So for that reason, when we're doing an enthalpy change with polystyrene cup, it's always advisable to put a lid on to stop any heat escaping. And the true, when you probably did a tin can experiment in your labs over here, if you've got a tin can, that's not the most efficient way. You're better off using a system here like we've got in this bomb calorimetry, and where you've got a good supply of air coming in. It's important to get air in, because otherwise we observe incomplete combustion in this experiment that we do in the lab. Okay, so they're the key details of the two practicals we're going to have a look at. We're just going to jump in. We're going to spend about 10 minutes looking at sort of some classics questions from past papers from the AQA exam board, based entirely on these two practicals. And let's see how we get on. So here we go. Read the following instructions. Classic sort of question is to try and get you to look at some instructions on an exam paper and see if you can work out how you could improve a reaction. Take a clean 250 cm cube volumetric flask, use a balance provided and a clean dry container to weigh out the amount of solid required. Tip the solid into a clean dry 250 cm cube beaker and add about 100 cm cube of distilled water. Use a stirring rod to help the solid dissolve, carefully breaking up any lumps of solid with the rod. When the solid has dissolved, pour the solution into the flask using a filter funnel. Add water to the flask until the level rises to the graduation mark. So these are the basic outlines, but the question is there any way to improve that? And we can look, there's a couple of key things that they've missed when doing this practical that we should consider doing. And there's a whole host of possible additions that we could have. So when we talk about weighing a sample, the best way of improving your weight is to weigh by difference. So that means to weigh a sample beforehand, then empty the sample, and then re-weigh the empty bottle afterwards. And then the difference between those two is going to give you your weight by difference. When you're putting the rod into the beaker, so these, I'm just going to go through all the possibilities. Every time you put the rod into the beaker, you may contaminate it in some way. So wash the rod would be a sensible thing to do. And that's going to be before and after use. Important here again with washing, because we want to ensure complete transfer. We could wash the beaker after we've transferred the sample out. So washing the beaker would be a sensible idea. That's going to ensure that all of our sample is transferred. You could also, here we're talking about a funnel. So we could also wash the funnel, because we could end up with samples on the funnel. And we could use as well, when we're talking, add water to the flask until the level rises to the graduation mark. Well, if you've done this in the lab without using a teat pipette, you probably overshot. Your teacher probably told you to go and do it again. So another way to do here is to use a teat pipette near the end to add small volumes of water. So you're going to have to look at these and think practically about what you can do to improve anything. And finally, as well, when you're making a standard solution, a good mix or shake the flask. Okay, so they're the key things. I think you only had to pick out 3, 1, 2, 3, 4, 5, 6, 7 possible ways of improving that experiment. Here's another classic way then that we're going to be looking at experimental detail in our titration calculations. We've got some data. Now, whenever you're doing titrations, you're wanting to get concordant results. Concordant means to be within 0.10 centimeters cubed of the result. And these results here, we've got a rough of 25.7. Notice a rough because there's only one decimal place. We've got 2 values, and the difference between these two is 0.15. So they're not concordant. So state what the student must do in order to obtain an accurate average titer in this experiment. Okay, and so they're going to repeat. That's your first mark that you'd be able to pick up here. But also, importantly, so to obtain concordant results, which is what we always do in our practical work. All right. Do just shout if you've got any questions. Put them in the blue chat room on our quick question page. Just drop yourself in to quick questions. You'll find the chat in this page. Please come and say hello. Ask a question if you've got anything as we're going through. Okay. Moving on then. Question 2. Here again, more titration experiments. Why would it be sensible to remove the funnel after it has been used for filling a burette? And that's simply that you might have had droplets of droplets of solution from the funnel could go in the burette. That would increase, or sorry, it wouldn't increase, it would decrease your volume measurement. No worries, Anon. 2123. I'm going to try and do these practicals, as I say, over the coming weeks. There'll just be short sessions, but there'll be lots of practice questions associated with those, along with the answers in the past webinar section on the site. Suggest one other source of error in using the burette to carry out a titration. The other, if you've ever used a burette, if you've ever filled them up, often one issue here is that at the bottom you get an air bubble, and you have to make sure that that's emptied. So that is always an issue with a burette. So make sure you empty the air bubble. These are just practical things that you're going to have picked up most likely when you're doing the practical work as you've been going through your chemistry course. Okay. During the titration, the inside of the conical flask is rinsed with distilled water. So here we're talking about rinsing. Whenever we're rinsing with distilled water, it's going to basically ensure that any sort of excess reagent is washed into the sample. We're using distilled water, so it's not going to affect the number of moles because there's nothing else in the water. It's just H2O. So it's going to ensure all reagents are able to react or able to mix. And so that's whenever we're doing any sort of washing, we're either going to be cleaning or ensuring complete mixing of reagents. Explain why adding this extra water does not change the volume of EDTA solution that is required in the titration. Well, that's not going to affect the EDTA because we've not added any more moles of the EDTA. Now, EDTA, if you don't know, is just a solution that we can use in redox titrations, but instead of EDTA, it could be any acid base, whatever it is. Okay, so it does not affect moles of reagent. Okay, so that seems to be in a funny place today. I'm not quite sure if that's moved on to quite the right page. I think I might have missed something off the bottom of the last page. Indeed, I have. I missed the bottom of the page off, which is a bit daft. Here we go, question 3. Now, this is an important distinction. Old papers discuss about percentage error. In the new specification, rather than percentage error, we seem to be using the term uncertainty in a reading. Okay, they're essentially meaning exactly the same thing. Just be aware that that is the difference, and how we measure the uncertainty is the error in a measurement over the actual measurement multiplied by 100. So in this case, for the pipette, we're told that it's 0.05 as the error that we can pick up here. So we don't we don't say it's plus or minus 0.5, so we don't go to plus 0.05 and down to minus 0.05 and then say the error is 0.1. We simply take the error as 0.05, we divide it by the reading here, and our pipette is probably 25. He's just looking in the question. The errors are taken into account. Let's make the maximum percentage used in these experiments. I'm just looking for the actual measurement. Presumably it's 25. I'm going to assume it's 25 because that's normally what we're using for pipettes, unless it tells us otherwise, which will give us a error of uncertainty, of 0.2%. When we do the burette reading, we got 0.15 and we're going to use 24.25. So here we are. At the top, the burette reading, we are 0.15 is our error, and 24.25 is the measurement. again times by 100, and that is to be I'm not actually, I just need to do that calculation to work that one out. And on 144, I'll tell you that in just a moment. So 0.15 times 0.15 divided by 24.25 times by 100 is giving us an answer there of 0.61%, hopefully. Okay, and on 1444. Yeah, it doesn't say in the question. The 25 in the previous question, that comes from the pipette volume. It doesn't actually give us the pipette volume in this question, so I'm assuming that the pipette volume is 25 centimeters cubed. Yeah, it's not the average volume of the pipette, it's just a standard volume that we tend to use. And on 1144, so all of today's webinars are being published through YouTube, but also on my website here. If you go to the web address, which is just below the YouTube link here, you've got drclays-alevelchemistry.com, which would take you to the page here. We're in quick questions, which are free weekly webinars. You click on that and you'll come up and you can see that you've got the embedded YouTube frame there. You're welcome to watch the chat box there if you're wanting to join in the chat. And we've also got here the OneNote pages, resources you can pick up what I'm writing on screen. If you're wanting to actually get all of the resources, these are available in the past webinars section. All of the weekly webinars, which are on the quick webinars, are in nice white to make them obvious, and if you click through onto those, you'll find both the enthalpy questions and the titrations and enthalpy questions, along with the titrations and enthalpy answers. Okay, hopefully that answers your question. Okay, back then to question number 4 then. So we've looked there a couple of questions based on titrations. We've got about 5 more minutes, and then we're going to call it a day, and I'm going to let you get off. Before we do, I'll just tell you what's going on in tomorrow's webinar. Here we've got our enthalpy of combustion. So here's our spirit burner. You might have done this reaction in school. A value of the enthalpy of combustion of an alcohol can be determined using the apparatus shown in the diagram. The calorimeter is held in position. Okay, so they don't bother drawing the actual the stand and that sort of thing. It can be repeated using a different volume of water that would result in a more accurate value for the enthalpy of combustion, because there would be a reduction in the heat loss. State a change in the volume of water that would cause a reduction in heat loss and explain your answer. So a change in volume. So here we've got to identify what the change in volume. Well, we can only either increase or we can decrease the volume. So if we decide to increase the volume, we're arguing. It's a bit of an odd question, to be fair. If you think we were to increase the volume here somehow, we could perhaps use a larger tin. So we might have potentially either we're heating up a large area of a tin, or equally, if we have got more volume of water in like this, then we're going to lose less water due to evaporation per volume. So there's a couple of odd answers to this. So small increase in temperature above room temperature, or increased contact between calorimeter and water, or smaller heat loss by evaporation from the surface, because we've got essentially a larger surface area in this question. That would be, I would have said, a reasonably difficult one to answer and to really think about on your feet there in the exam. Bear in mind that if you're thinking about uncertainties, this isn't in the question. If we think about the uncertainty where we're doing the error in a measurement over the actual measurement taken here, times by 100. Well, the error is going to stay the same because our thermometer is constant. So to decrease any uncertainties, we need to increase that measurement. So we'd want to heat it to a higher temperature. Okay, moving on. Again, another question then about enthalpy changes. The alcohol 2-methyl propan-2-ol reacts to form esters that are used as flavorings by the food industry. So here, this is quite possible, a sort of question you could get in your paper 2 or your paper 3. A student carried out an experiment on a pure sample of 2-methyl propan-2-ol to determine its enthalpy of combustion. A sample of the alcohol was placed into a spirit burner and positioned under a beaker containing 50 cm³ of water, very much like the experiment we've just seen above. Spirit burner was ignited and allowed to burn for several minutes before it was extinguished. The results for the experiment are shown in table 1. So here we go. So here's some experiments from the experiment explained. So here, this is really some knowledge. So this isn't so much a question there about experimental technique. What I'll do is I'll simply put the answer up there. If you were to run it through, you should get 5,706 joules, or 5.7 kilojoules if you were going to give it in kilojoules. Either answer is correct as long as you are using the right unit. Calculate the amount in moles. Okay, so this question here is really here just to show the sort of question we might get associated with practicals. You're then asked to develop this one further and to try and get a total answer, which is delta H is equal to minus Q over N. If you run this one through, hopefully you'll find you get minus 1921 kilojoules per mole. I'm not going to work too much on the theory here because it's something that we will look at in our revision lectures rather than the practical. Isn't it a minus? Okay, and on 8863, nope. Your temperature values here, when you're talking about that, it is going to be the final temperature minus the start temperature. The reason here is Q is a measure of the energy in the external surroundings, whereas delta H is a measure of the energy within the bonds. Those are equal and opposite. So the external surroundings really are being heated, so it really is an increase in energy to 5.7 kilojoules. Okay. Again, this question seems to have popped up here. Is in the enthalpy questions. Once again, this is really theory rather than particularly practice, but just for completeness, so you can sit there and have a go at another time, because I want to look at practical details. It's minus 264 kilojoules per mole minus 1. Okay, now here's the actual practical question, an accurate value that we're asking for. Again, here we've got the overall percentage error. So remember, rather than percentage error, we're probably dealing here with percentage uncertainty in the experiment, rather than, as we've been seeing in previous years, talking about percentage errors with percentage uncertainty. So using the value and answer from part B to calculate the overall percentage error of the student's experiment value for the other of. So we've got minus 2422 is the accurate. So to get this, we do our answer, take away the actual answer over the actual answer, minus 2422. Again, you should get an answer around about 20.7%. In this one, sorry, times by 100, we should get an answer around about 20.71% for this question. In this particular one, we can ignore the plus or minus that we may get. Okay, how could we improve the experiment here? Except that would reduce the errors due to heat loss in the student's experiment. Oh, sorry. Suggest one improvement that would reduce errors due to heat loss in the student's experiment. So there you could come up with a host of different ways. You're looking at the practical. You've got to think of a way of reducing heat loss. So if you've got a burner, in fact, I'm just going to go back to the previous page here that we've got, because we've got a nice picture. If we're doing that, if you can make some sort of shroud somehow to go around it, something that perhaps looked like that to stop any or reduce the heat loss to the environment, that's likely to be a good answer. Simply some sort of sleeve or a carbon tube. Not a carbon tube, a cardboard tube is probably going to help. Something practical which is going to reduce the heat loss. Perhaps a lid on the tin, although that might be potentially dangerous because you're going to cause it to bubble. Suggest one other source of error in the student's experiment. Do not include heat loss. So classic one here, if you're talking about a combustion experiment, is you've got complete combustion, but you also have incomplete combustion occurring. And incomplete combustion is less efficient than complete combustion. And so is an error with this particular experiment. How can you improve it? Well, you can increase the airflow. It's not asked for in this question, but increase the airflow, or more importantly, the oxygen flow to the sample. Okay, there we go. There's the rest of that question. Anhydrous copper sulfate is not used as a commercial de-icer. Okay, so right, here we go. Here's some data. This is an enthalpy of reaction here that we're going to measure. We got two different bits of data. Notice we're about 19.5 here, and then we jump up to about 24.6 and go down to 23. Key things, we got a plot. I'm not going to draw this accurately, but you will get marks for drawing it accurately, obviously, in the exam. Key things here are to not make your graph too small so you can't read the data. What do I mean by that? Well, you've got a graph of data here which was from 19.5 to 23. So sometimes what we tend to do is we come along and we go, oh, I'm going to draw my plots and I'm going to have it from 0 because that's the start temperature and go up to 23. And what we end up with a tiny little bit of data up here. And what this does is it reduces the size of our measurement and increases our error. So when you've got data like that, where you want to increase the amount of information where you plot it, start your x-axis at a sensible number. So a sensible number is probably 19 here, and 23 we'd end up, and then we got time along the bottom. So we got 0, 1 to 10. You've obviously got to draw this accurately. We'd then have 4 plots, 3 plots like that. We would then jump up to whatever it is, 25.5. We'd have some plots that go down like this, and then we would draw 2 lines of best fit in this experiment, and it's where we're mixing 2 samples together, and we get a nice big measurement to take for our change in temperature. Make sure you label any axes correctly and give an appropriate scale when you're doing them. Okay, so they're the key things that we want to think about when we're drawing graphs. Doesn't seem to be anything on that page. Okay, then so some measurements about taking taking measurements. I'm just going to fill these in for you so that you've got something to work from if you want to sit down and have a crack at this. So 19.5, acceptable answers for after mixing is 26.5 plus or minus 0.2. So this is all can you read from a graph. I wouldn't be surprised if they put graphs in your experiment somewhere or other. The answer here is C minus B. And then you've got to use Q equals MC delta T here, where delta T you're taking from this answer. M here, remember, is the mass of water, where we got 1 gram. I can't remember what volume it said it was using. We'll go back and have a quick look, shall we? So we've got 25 centimeters cubed of water. So there our mass is 25 grams. We're given the heat capacity and delta T, and we work out an energy in joules. Calculate the moles of calcium chloride and use your P, E and F to calculate a value for the enthalpy change in kilojoules per mole. So this one is finally going to be delta H is equal to minus Q divided by the number of moles. Okay. The final one we're going to look at now is on page 10 here. I think, and so just some simple sort of ideas about what we can do in order to make ourselves safe when we're doing experiments. So one reason why is you wish to prevent unreacted chlorine from escaping here when we're looking at chlorine. I've missed some of the question out, haven't I? No, I haven't. Here we go. Explain why it's important that the reaction meter stir when recording each temperature, and that's to ensure the solution is all the same temperature. Chlorine here, ideas, safety. Chlorine is toxic. And finally suggests one hazard of using apparatus suggested by the student for this experiment. Okay, so there's chance of explosion here as we're looking at, because we're now heating a glass tube. Okay. There's heaps more questions. If you're wanting to join, if you want to see the rest of the site, if you go along and check out the past webinars section, you'll find today's webinar is still available here. You can, as I say, you should be able to pick up the OneNote pages from all of the quick question webinars, which will come up in a screen that looks a bit like this. You might need to change from the quick NMR, which was our first one. We're on titrations and enthalpies. All of the equations will be there that we've been looking at through the sessions. If you're a member, you'll also get access to the titrations and enthalpy questions. Heaps more questions here as we're going on, so you can see plenty more to be practicing. If you want to work on any more of those titrations and enthalpies, and as well to go with those, you'll also find the answers. Tomorrow night, we're carrying on with the rest of the organic chemistry. Sorry, not organic, the physical chemistry from paper 2, which is the organic paper. So if you're a member, please do join. You will sorry, if you're not a member, please do join. We've got all of the resources available. We've got heaps of past paper questions coming up tomorrow night. I've just finished today putting all of these past papers. I think there's about 50 pages there. I wouldn't print them all off if I were you. And we'll be looking at rates of reaction, a bit of KC equilibrium equations, and as well the A2 level initial rates method, and so on. All right, so that is tomorrow night at 8:30 p.m. If you're not a member, simply click join or drop me a line. It'd be great to talk to you. I hope you found this session helpful. We will have another one next Wednesday. We'll look at some of the more practical techniques other than titrations and enthalpies. I'll think about that between now and next week, and I look forward to catching up with those who are around tomorrow night. That's all from me. I'm going to say goodbye for now and have a really good evening. I'll be around in the chat for a couple of minutes. Good night.